We've split this into two sort of 10-minute talks. We're going to try and cover, Malcolm and I, cover as much as we possibly can in those two 10-minute talks. We probably won't cover the whole of the scope and the whole of the phenotype world. So we're going to try and do as best we can in the time available. So I'm just going to do a quick reminder of the scope of the program, Phenotype and Trait Measurement Technologies. Malcolm's an animal physiologist, I'm a research engineer, that's our background, so we become slightly complementary. We're going to concentrate obviously on the challenges in the animal sector, and there is a slight government health warning in that we're covering from, we're in an unusual position of covering from the industry's point of view as wearing semi-academic hats. So we will try and cover as much as we can. Malcolm, with his classical background in education, has provided me kindly with the definition of the phenotype. And it's quite interesting, I'll be laborious and go through this, but it's quite interesting to actually get the origin, the definition, and get into our heads what the phenotype actually is. It's the collection of all its manifested attributes, and it's the joint product of the genotype and the environment and the interaction between the two. And it's all observable physical or biochemical characteristics of an organism as determined by both genetic makeup and environmental influences. It's a bit heavy. And it may be an expression of specific traits based on genetic and environmental influences. And if some of you, or most of you, can read the words at the bottom, the extended phenotype, in the sense that the phenotype does not stop at the skin, which means that the animal itself may actually have an influence on the environment beyond the animal. Think about wastes and greenhouse gas emissions as an isolated example of that. Sorry, moving on. The objectives, improving identification and measurement of key production and quality traits, development of tools and technologies and systems, better understanding the application of genomic information, better management decision making in the field, data capture and integration. I'm repeating more or less what David has said earlier on. And it's aimed at you guys, and you guys are a combination of these two things, we hope. Providers of technology that can be used to monitor and record traits, organisations providing or developing sensors, image technology specialists, etc., and those involved in agriculture and related fields, both in the commercial companies and research organisations like yourselves, who could develop these, be end users of these technologies. Okay, just a reminder. You'll have this in the packs, but this is the kind of the scope of the areas that are going to be addressed in this call. Fertility, feed conversion efficiency, carcass and milk quality measures, disease resistance, functional management traits, improving animal welfare, greenhouse gas emissions and environmental impact, and as was mentioned earlier on, going further down the chain to things like shelf life, yield wastage, quality, nutritional and food safety aspects. Okay, generic qualities of systems. Just a quick intro slide on the systems. Now this may cover most of the potential application of technologies. It may not cover them all, but those that covered are in the farm area and transit and slaughter. Simple, operation, and both time required to get a result. Reliable, robust, cost-effective, and compliant with any regulations. Minimal interference with routine practice, and ethically acceptable. These are kind of bullet point wish lists of what we'd like to see at the end of each project, I would guess. A combination of established proven technologies deployed in a novel way, cutting-edge technologies, which we might hear about later, and novel applications of technologies that may exist in another industry sector like ours. Fertility. Just a quick series of bullet points on fertility, not covering everything, but just as an example of the sort of economic consequences in the dairy sector, it can cost up to £5 per animal day. Beef can be up to similar costs. Different ways that can be measured. You can look at something like a hormonal component in, for example, milk progesterone or other hormones, or you can measure the behavioural component of fertility when the animal cycles, and you can look at other specific behaviours which are aligned with that. Now, so the examples of current systems in the market already, this is what's called the Herd Navigator system, which is marketed by De Laval, and measures, it's a dry stick technology, so you have to grab a sample from milk and take it to the machine, but it uses a series of reagent type measures to produce measures that are related to fertility. Also does estimations of mastitis and ketosis. There are other activity-based sensor companies producing product at the moment, and this is something called the Silent Herdsman. I think there's representation here today from that company, which is marketed currently to detect estrus. And this is an activity-based sensor which is already deployed on a number of farms. There's the Ice Robotics local company producing something called the Ice Cube. Any represent? Yes, there is from Ice Robotics today. And there are a whole range of other variants on the same theme that record activity. This is an Israeli-derived technology that's marketed Europe-wide. So the generic sense, they monitor components of activity and process that. So I suppose the challenge is to get as close to 100% prediction as possible in this area certainly for the ruminant species. Feed conversion efficiency, well, just a headline figure. I think these are reasonable estimates, so somebody may correct me if I'm wrong, but very, very large numbers of millions of tons of processed cereals in the world, over 1,000 million, over 1 billion tons. And obviously, as David mentioned earlier on, there's going to be competition for cereals with humans potentially bioenergy in the future. So it makes feed conversion efficiency critically important in the future for both management, genetic improvement, and efficient use of an increasingly expensive resource. So how do you measure it? Well, individual feed conversion efficiency is measured in experimental facilities, which is fine for a testing station if you're testing pedigrees or nuclear genetic stock, but not for general industry. What you measure are individual intakes, diets, and growth rates are recorded. And the challenge is how to do that cost effectively for different species. And another additional challenge is how do you measure grazing animals? It's okay to do it in a shed where you have nice constraints, but to do it for grazing animals. Other measures. Now this is a typical facility, this is actually ours, where you're measuring the intake of each animal, weigh cell recorded and electronic ID, and you get a daily record of the intake of the animal. This is another facility that's comparative, it's I think originated in Canada. This is a pig equivalent that measures the individual pig intakes using exactly the same principle. And again, another pig installation using exactly the same principle. Again, they're quite relatively capital intensive, and you cannot conceive of doing that commercially on a farm. So how would we do that? I'm posing questions rather than giving answers, I believe. Carcass and milk quality, optimizing the carcass for the market, reducing waste, meat quality attributes, target specifications for milk quality, dairy production traits. These are all standard wish lists from the industry. Pardon me. Systems for estimation of carcass parameters. Some of them are deployed already. Milk quality, online somatic cell count, protein and fat. Again, potentially deployed. Dairy animal traits, a very interesting area. And just some examples of what's available on the market at the moment and coming into the market. And we're starting to see developments of these kinds of systems that effectively measure, using video technology, the traits on the carcass, not just the classification, a whole range of other parameters relating to yield. These are starting to come into the marketplace and being developed. A project sponsored by Quality Meat Scotland and the Scottish Government has realised the ambition of being able to automatically place sensors on the carcass using an autonomous robot. The question is, what would you actually attach to the end? What other things would you want to try and sample or get or measure on that carcass? Moving across to milk, this is a machine which actually measures the components of milk, but it's a laboratory-based instrument. In an ideal world, you'd want to put that in an individual milk line for an individual cow and get the measurement at an individual level to capture the phenotype. Another random example of monitoring animals for potential lameness. This is an American system which actually is reasonably capital intensive, but relies on reaction forces in the base, and the animal ambulates over the top, and it measures differences, and it computes a score on lameness. Again, debatable in the kind of farm structures that we have, whether that's cost effective or not. Again, can we look at something that's simpler and cheaper? Disease resistance, such a huge area. Diseases across species, wide range of classifications. How do you measure symptoms? Could you measure it direct? Or could you use proxy methods, something like behavioural science? Can you look at precise location? And there's a company here that can do that. Can you look at water intake, perhaps even breath sampling? It has to have ease of measurement, no or minimal intervention. And I've cited a couple of examples here. I'm dipping my toe in the water of the aquaculture sector that I know very little about. Salmon sea lice infection is a big problem, and liver flukes is a significant problem. So these are how they present. How would you measure that? How would you measure that? Rushing through to greenhouse gas environmental impact. Most of us or all of us know about the problem with ruminants, particularly produce methane, nitrous oxide, which are the greenhouse gases called multiplier gases. In future, obviously, there's likely to be an increasing pressure on reducing ruminant greenhouse gas output, although other species also contribute. Direct and accurate individual measurement is very expensive. Could we consider proxy measures, or even measures within the rumen? So this, I don't know if it's low, most of you can see this here. This is a slide, this is a picture of a greenhouse gas measurement facility. It's a containment chamber facility that allows you to capture over a time period the complete emissions of an individual animal. But again, it's expensive. So how can we actually do that more cost effectively? Are there technologies, and these are two typical examples of technologies that are on the marketplace at the moment for measuring parameters within the rumen. Can we extend those and get more direct measures of methane emissions, shall we say? So just posing a question again. Shelf life. That's an interesting thing if you're going to capture the phenotype, because you need traceability. There's no point in getting measures in shelf life if you can't trace it back to the animal. So obviously dietary influence. What's interesting in shelf life? Colour stability, risk of meat becoming what's called darker and dry or pale soft exuded. And is there a relationship between monitoring stress pre-slaughter of that animal and any of these characteristics? Well, it's hypothesized that there is quite a strong relationship. So could you measure pre-slaughter stress, and how would you do that? So these are kind of a couple of contrasting examples of what I call DFD and normal, and you can just see the colour difference. Yield and wastage. We have obviously a producer would like to obviously estimate the target specification for their market as best they can. So how would you do that? At the moment, it's potentially done by eye in some instances in the ruminant sector. But would it be better to have a more automated system to do that? So think about live animal yield estimation. We have in the sector, we have the ability to compare that with accurate methods. I call it the gold standard, which is computed tomography. It gives you an accurate indication of muscle yield, fat yield, and bone. And can we use other techniques such as ultrasound, yield fat estimation, and prediction? Can we look at imaging technologies to quantify both growth, yield, and condition? Can capture all of these and encapsulate all these in some form of imaging technology deployed cost-effectively locally at the producer end? It's 30 minutes. Sorry, I better run. Okay. Some examples of some of the technologies that are being developed or on the cusp of being deployed commercially. A pig and a cross-section of the pig with a CT scanner, and a salmon, and those that you can see at the bottom, still alive, I think, if somebody can confirm that. Yep, going through the CT scanner with cross-section, but I think there's more to be heard about that later on. Quality, flavour, texture, nutrition. Consumers still willing to pay a substantial premium for sensory quality. Rapid objective measures of sensory nutritional weight still required. And this is the standard setup at the moment, very costly, using humans as the standard. But some technologies show promise. I'm just going to rush through this. Make a comment about the data. A component of the actual call is associated with data. So, data islands, information that's stored in different places that could actually have synergistic purpose if we pull them together. And running through again desirable specifications, this is reiterating one of the first slides, is robust would be my call if someone who's worked with animals. You have an animal challenge and an environmental challenge, and certainly you have a primary processing challenge for anything that's deployable. And you need ease of interpretation, and you can't overload the user with data. So you need this kind of robustness, and not that kind of output. And I have, sorry, I'm now going to hand over to Malcolm. It's kind of a bit of a double act, and I'll take questions at the end. Sorry, it's in a bit of a rush.
For the second component of the presentation, I'm going to focus pretty much on the central theme of the core, which is the development of measurement techniques, novel measurement techniques and integrated measurement techniques. And I hope to apply that to functional management traits and indeed to animal welfare, because those are the two remaining areas of the core that David hasn't addressed. I'll talk a little bit about some current systems and then some challenges and opportunities, being highly selective on some of the technologies that I think can prompt discussion later, but draw attention to the fact that novel technologies perhaps is where we should be going with this particular core. But there are some essential foundations that we need to look at. For the development of new measurement systems, it's absolutely vital that we don't talk generically. We've got to identify specific measured variables that are of importance to us. And in this call, we need to demonstrate that there's an association between those usefully measured variables and the key or critical production variables. We then need to have proof of concept in terms of sensor design and whether it measures those variables. We then have to validate that as an application in an industrial setting. In other words, full commercial evaluation. And that's where I believe we should end with our new sensor and new measurement systems. We'll address areas such as production efficiency. We can look at pure outputs, we can assess profit, but our systems must underpin improved production efficiency, and as David has illustrated, we can use new measurement techniques to look at product quality. We also vitally need now, in overall animal production, to look at animal welfare, not just because of our ethical concerns, but because that will provide us with some market advantage in the future. All markets will improve with higher welfare products. So measurement techniques that allow us to create higher welfare products are important. Obviously we need to address environmental considerations, and measurement techniques and sensors for that purpose are vital. And of course many of these types of new measurements are to underpin regulatory obligations. We all know, for example, about 1099 that came in on the 1st of January. Where might we apply all these new measurement techniques? Well, clearly on farm. We can measure the more common phenotypic traits like growth, etc. But in parallel, and for control systems, we should be looking at conditions, the environments of the animals, the welfare. And that can be applied to a key element of animal production which causes so many losses, transportation of slaughter animals. We also need to apply new measurement techniques at slaughter and in processing during the ante-mortem period related to ante-mortem stress and therefore product quality. But we also need to look in the immediate slaughter period, methods of slaughter, etc. And finally, all that needs to be correlated with the new measurement techniques for product quality. What might we measure? Well, obviously animal performance, typical phenotypic traits, but also the resources available to the animal and the conditions to which it's exposed. These are key features which sensors can monitor and contribute to the control of those conditions to optimise productivity. The same applies to looking at the efficiency of the procedures and the processes that we apply in animal production. And of course, if we can develop sensors to examine animal stress, the induction of pathology by stress and conditions or through disease, then if we can do that in an automated way, for example, there are certain breath analyses that might allow us to do that in an automated process, then we can improve the well-being of the animal and ensure its product quality. And finally, we need to correlate all of those features with product quality and product chemistry. What might we assess? Well, clearly impacts of all the areas I've referred to upon productivity, efficiency, quality and welfare simultaneously in holistic models. We can apply that at the farm, during handling and transport, at the slaughterhouse, and in the case of product quality post-mortem. What does all that mean? Well, we're now talking about multiple sensors with multiple functions. They're the inputs to precision agriculture or precision farming, and also to new expert systems. Here's a definition of precision agriculture. What's important about that is it's fully integrative, and most importantly of all, precision agriculture, precision farming is in the field, as was stressed in the description of the core. It only works obviously in the field. That's a summary of the process. I don't mean to go through all of this, but it's quite clear that the new measurement techniques and sensors we're talking about can contribute to monitoring inputs, but also to monitoring outputs, and give us a very successful data-based modelling approach to productive agriculture. So what do we measure? Well, to reiterate, some of the resources, the environment, but also the performance of control systems. We might look at the environment in terms of deterioration. That might apply to air quality, water quality in agriculture, or bedding, for example, in intensively produced animals, or litter. We also try to measure some indicators of pathology and disease and indicators of stress and welfare. Specifics might be changes in food and water consumption, monitoring temperature and humidity with better designed systems in the production environment, bedding and litter quality, which I referred to. Most importantly, as David described, animal activity and behaviour can tell us a great deal about the animal's welfare, but also about its health status. We might monitor noise levels. In intensive production, there are characteristic noise levels which, through frequency analysis, can tell us about the well-being and the activities of animals in that environment. And we can look at ventilation throughputs in enclosed spaces and their control, and through analysis of exhaust gases, learn a great deal about the animal's behaviour and well-being. We can do all of this with existing technologies, which we're talking about today, and improving those technologies. But what I would emphasise is we need to think about novel technologies and novel applications of existing technologies. And perhaps most important of all, integrating different approaches into single precision farming systems. I'll look at a few examples briefly. We might look at a web-based expert system. One is in existence for looking at pig diseases. We can see that the model in that consists of over 300 rules, 202 images, which with the correct inputs through the graphics can diagnose 54 types of pig disease. That's a step forward. We can modify that, and that can be informed by the creation of novel sensors, novel measurement systems. I mentioned sound analysis. Sound monitoring is already used with frequency analysis to detect coughing pigs. So you can detect the onset of certain respiratory tract diseases monitored with a parallel monitoring of environmental deterioration to detect and diagnose particular problems. We might use other technologies like rumen boluses to detect not only changes in pH associated with specific pathologies such as subacute ruminal acidosis, but we might use those to look at body temperature, oxidation state, and a number of other potential variables. And this leads us into the area of wireless technology, where we can use all such devices to monitor the physiological status of the animal and transmit it to a central station for storage and processing. And they're the kind of technologies I think we should be looking at today. Another area is thermal imaging and imaging in general. This is the use of thermal imaging in the detection of subacute ruminal acidosis by looking at temperature differentials between the flanks of the animal over the dorsal sac of the rumen as compared to the small intestine. And that temperature differential in an automated system can indicate changes in ruminal activity and therefore the onset of SARA. Other areas of physiological status that we might create new measurement systems for. We've heard a little bit about estrous detection through activity and behaviour, but we might again look at deep body temperature changes through novel surface-mounted wireless techniques that could be attached to the outside of the animal, perhaps within an ear tag, in order to give us an indication of things like estrus or the onset of parturition. And parturition could be monitored again by similar technologies if we use something like the electrohysterogram. It's possible to create sensors and wireless technologies that would allow us to do this. Heat stress and cold stress, obviously we can measure deep body temperature, but there's a move towards having sentinel animals in all systems and in animal transport that would allow, again, animal-friendly sensors to monitor deep body temperature for a number of purposes. All of these things constitute diagnostics for remote monitoring using wireless technologies. Estrus detection systems are already in place. We know from bore visits, for example, we can measure estrus by the acceleration. This is the collar that David described. But we can take activities, for example, bore visits, and incorporate them into well-defined models. And this particular model which incorporates Markov transition probability, allows us to identify those animals coming into heat. So what about the welfare area? Are there any other technologies that we might employ? Well, certainly image analysis, monitoring physiological stress in sentinel animals, quantifying activity and behaviour by automated systems, and again, analysing sound and noise levels, because frequency analysis will allow us to determine things like alarm calls in animals which might indicate possible distress. This is already used on some one-day-old chick transporters where temperature stress is identified by an increase in alarm calls. We could look again at thermal imaging. This is thermal imaging for piglets. It's easy to identify piglets that don't go quickly to the teat, piglets to cool down very, very quickly at birth, and so their welfare can be monitored by thermal imaging. In contrast here, we see some pig production in Australia in a massively overheated house where these very hot piglets are actually collapsing over an air inlet. So an automated system using imaging allows us to identify this. Image analysis for looking at, for example, the kinematics of gait abnormalities in poultry offer another option, as does thermal imaging to look at joint inflammation and hock problems in turkeys, or inflammation associated with tail docking in piglets. Coming to the final straight, image analysis might also be used at flock level. This has been employed by Marion Dawkins in her studies, where simply she uses optical flow, which measures the velocity of an image in motion in front of a camera. This illustration shows how we calculate the speed of this car from this shift and the optical flow. This is used in broiler flocks in order to look at changes in optical flow associated with changes in activity, lameness, feeding pattern, etc. And finally, we might look at behaviour. There are systems in place which are actually part of precision livestock systems, which look at aggression, record aggression, and can be used to monitor and change that. The very final variable I put forward to you is something like heart rate variability, which is a primary and powerful indicator of stress. It can be measured by wireless surface-mounted systems, particularly in sentinel animals, in housing and in transport. So, in summary, I think there's a large number of new measurement techniques we can use to address many of these crucial production issues. We can also look at improved environmental monitoring, which we can incorporate into our precision livestock systems. We can do so by also including sentinel animals in production situations and in transportation with physiological status monitoring. We can then integrate the environmental and animal monitoring into grand systems, and I think that can be supported by the future creation of many new biosensors for looking at all the variables we're interested in. I thank you for your slightly prolonged attention. I hope that was stimulating. Thank you.